Morning, everyone. So today I wanted to review with you some of the major concepts that we saw in our kinematics chapter. This chapter was all about motion. We introduced terms like distance, speed, acceleration. We started seeing some of those equations. Hopefully this will serve as a nice review for you. So we have our kinematics. Kinematics is essentially the study of motion. How far, how fast, those ideas here. Turns out in physics, quantities can be separated into either what's referred to as scalars, or they can be separated in what's called a vector. In terms of the scalars here, they typically like saying scalars have magnitude only. I remember always being scared away. What do you mean magnitude? Magnitude just means the number, right? So if, for example, I have 5 meters or 10 meter per second, the magnitude part here is just the 5, just the 10. Obviously, depending on what we're measuring, it has to come with its units as well. For vectors, they also have a magnitude, but vectors actually add one other feature to it. They have this magnitude or size, but the key difference here is they actually end up having a direction as well. They actually have a certain heading. So this is why vectors can be represented with an arrow. The size of the arrow, so the length of the arrow, actually represents the magnitude. If this magnitude goes from 5 meters to 15 meters here, the arrow should be longer. The arrowhead, depending which way we're pointing, it gives you the direction. As we review our vector addition negation, again, we're going to have some conventions that we follow here. Vectors, because we're actually changing direction, it became not so easy to work with. So, for example, here, we may have 5 meters east or 10 meter per second north. You notice that there's a certain directionality to it here. Sort of the unfortunate fact here is sometimes I don't write down the words east or north, so I just use the positive or negative convention here. Well, positive is used to imply east, whereas positive here is used to imply north here. So sometimes we just use positive or negative to actually indicate the direction. More on this in a little bit. So as we start separating our quantities here, we started looking at the how far. In terms of how far, we started off with just distance. Right? Distance just covers how far away objects are from each other. Because this one here is the scalar form, we're going to put just d for it. Displacement has that sort of blindfold on, blindfold off analogy here. It's how far I'm pushed from start to finish. And this one here was d with an arrow. This one here actually had directionality to it. So let's just think through our example again. Let's imagine we had a top view of a room, and let's say we have a person standing in the corner. They're going to walk, let's say, 5 meters north, and then walk maybe 7 meters east. Okay. So in terms of distance, it's just sort of the total number of steps. So the person here, they walked 5 meters. I don't really care. They actually changed direction and they walked another 7 meters. So in total, they're 12 meters. Whereas for displacement now, we're going to say, well, wait a second. If I put on a blindfold and I notice the person started off in the corner, I don't actually watch the person do this. When I take off my blindfold, I end up realizing he's over here. He's actually not 12 meters away from the starting point because there was actually a change in direction here. In fact, what we would do is we'd actually use Pythagoras. We'd figure out, although the person never ended up walking this hypotenuse, the displacement, how far is he pushed from where he started with? We're going to go based on Pythagoras here, the root of 5 squared plus 7 squared here. Root 5 squared plus 7 squared. That gives you, oh, you're actually only 8.6 meters away from your starting point. Because there's a directionality to it, I know sort of our compass system, northeast, southwest, I know it's northeast, but I might want to tell you what the angle is. For the angle, we had recapped, we can use inverse tan of, let's say, 7 over 5 in this situation. Make sure your calculators are in degree mode for this. Inverse tan of 7 over 5 gives me 54 degrees. From the pure northward direction, I start aiming east from there, so east of north. Okay, so we have our total number of steps. The person literally walked 12 meters. But because there was a change in direction, because he twisted here, he actually is only 8.6 meters away from his starting point, and he's actually off at an angle. He's not just north or just east. He's at this 54 degrees away. So in terms of displacement, we saw we actually need to do the Pythagoras here. So he's actually 8.6 meters away. This is his displacement. This is how far he is away from his starting point. But the directionality part of it actually gives you, by the angle here, I could give you this angle, 54 degrees, or I may have actually walked 5 meters east first and then north this way, I might actually tell you this angle, because these angles here are complementary, they add to 90. I can go 90 minus this 54, give or take a little bit of rounding here. I could equally well write it 36 degrees north of east. Both are perfectly fine. There's a size with the unit, and there's a direction to it. Okay. Now, for a lot of the starting questions that we did, many times distance and displacement were the same, or speed and velocity were the same. I want to just make a note here. So in this example, the distance and the displacement, we saw that they're different, right? And the reason why they're different, well, I walked 12 meters. How come the displacement, I'm not 12 meters away from where I started? I've been emphasizing here because you've changed direction. So let's just actually write the opposite here. Distance and displacement are the same only if the direction doesn't change. Okay? Well, the difference between a scalar and a vector was the whole notion vectors have to have direction. Well, if I just head in one direction, I walk 5 meters, then I walk 7 meters in the same direction, obviously I'm going to be 12 meters away from where I started. So using that sort of similar logic here, we have the sort of distinction between speed and velocity. Speed definitely tells you how fast something is. We're going to use v, because later on we're going to use velocity for the vector form. The velocity here is essentially, it's your displacement divided by the time, right? This is where we actually start getting our kinematic formulas again. And we're going to end up putting a v with an arrow above that there. Okay, so back to this example. Let's say this whole motion took 10 seconds, just for argument's sake here. Well, the speed is, well, you actually walked 12 meters. If I tell you now it took 10 seconds, well, that's going to be 1.2 meter per second. On average, you were walking every second 1.2 meters. Okay. Whereas for your velocity, right, with the direction here, because in the end I end up only getting 8.6 meters away from where I began, if I have my displacement at 8.6, if I imagine you walking in this diagonal, which I know you didn't, but if you got 8.6 meters away from your starting point and it still took you 10 seconds to do it, you'll notice your average velocity is different. And again, what we have here, sorry, 0.86. What we have here is the speed, 1.2, is different from the vector, again, because there was a change of direction. This part here did give us our first motion equation. We usually call this a basic motion equation. Basic motion, usually the terminology we're going to use is uniform motion. And uniform motion essentially stands for a constant velocity. It's not that you can't be moving, but your motion is just constant. You're not speeding up or slowing down. We later on added in, there's actually no acceleration. So the basic motion equation was essentially, it actually is just a manipulation of this velocity formula here. The velocity is defined as change in displacement over change in time, right? And you just rearrange that there. What if I wanted to just re-express it for the d here? The d is actually equal to v times t. And in the case here, we're constant velocity, we just have one velocity. Sometimes in formulas they say v average for there, but that is a basic motion equation. Okay. If you know the speed, if you know every second I get 0.86 meters away, give me 10 seconds, I would walk the whole 8.6 meters in this diagonal direction. We saw that the situation was a little bit more interesting when we started looking at acceleration, because you can actually accelerate in different directions here. Let's say your velocity is going this way, and let's say you step on the pedal here, and the acceleration is also in that direction. Whenever acceleration and velocity are in the same direction, that implies a speed up. Right? Things will, in that terminology here, they accelerate. For me to slow down, right? In words, we're going to say decelerate. Usually there's a negative acceleration. That's when my velocity is trying to go one way, and my acceleration, maybe I step on the brakes, or I encounter a wind that's blowing in the opposite direction. Depending on the size of these ones here, usually I don't stop in my tracks right away. It takes me a little bit of time to actually slowly come to a stop, but definitely I am going to be slowing down. Right? So as we started throwing in acceleration into this here, that gave us one of our kinematic formulas from our formula of acceleration. Acceleration is a change of velocity. How does that velocity change versus change in time? Every time you have this delta here, that delta, so it's a Greek letter here, that delta actually means change in, and change in is always written final minus initial. Right. Now we're going to be a little bit clever here. Usually when things start getting interesting, so let's say the object was just sitting, maybe it started off at rest. Rest means 0 meter per second. As you start stepping on the accelerator and as you start having this velocity, I'm going to call that t equals 0 seconds. So if the ti is 0, and let's say it does this for 10 seconds, 10 minus 0 would just be 10. That's just the time interval. So I'm just going to leave that there as 0. I can bring the t term up. So a times t is equal to vf minus vi. And what I'm going to do is I'm just going to rearrange it here. I'm going to bring the vi over, so it's going to be vi plus at. So vf is equal to vi plus at. Right, so that's basically from the definition of acceleration, just slightly rearranged there. This is our second kinematic formula, which actually introduces that acceleration term as well. It's just on the formula sheet here. They usually use in physics here a naught symbol. It's like a tiny little O. That v naught here is the symbol they use for initial velocity. It's your starting speed. If this is at rest, I can assume it's 0. The vf here is just going to be written as v, and that one there is going to be your final speed at a time t, or at the end of your pathway when you're sort of done accelerating. This is the speed that you leave at. So just care for the notation. You're more than welcome to use vf and vi in this. We saw that your basic motion equation, the d equals vt, was actually a slight simplification of a bigger kinematic formula here. We actually had d is equal to v naught t plus 1/2 at squared. So if there is no acceleration, if the a is actually 0, right? So if a is equal to 0, 0 times anything, it just kills that off. The velocity wouldn't change anymore. I just have v times t. I actually get my basic motion equation back. But what if there actually was an acceleration? Basically what happens here is I'm going to do v times t. I'm going to say take your starting speed, multiply that for the entire time that I actually travel for, and then because there is a either speed up or slow down, that's actually going to slightly adjust the displacement again. Either slightly more if I'm accelerating, slightly less if I'm decelerating. What we ended up doing was, in our notes, we put those two formulas together. We gave one last expression, which was this v squared equals v naught squared plus 2ad. All of these kinematic equations, they sort of work together here. Some hints of sort of when to use one over the other. You'll notice the bottom equations, these are all in your formula sheet. The bottom equations have to do with v final. So either you have v final already, I know this number, great, that's one variable I don't need to look for, or they're asking you to calculate v final, that's when you would use that. Then another distinction here is, you notice this first formula here deals with time. The second formula also deals with time. This formula here has nothing to do with time, so if I have the time, I might want to use the first two. If I have only the displacement, I don't really know the time of travel here. This formula here using displacement, this formula does as well, where this formula doesn't use displacement here. So those are just some nice hints. Pretty much you can use the equation if there's only one unknown in the overall problem. So let's just try a quick kinematic problem here. I want you to calculate the displacement and time for a car moving at 60 kilometers per hour to come to stop in 30 meters. Okay, so I would encourage you to try it out for yourself here. I would always like starting off with a picture if we can. So we have a car, right? Nice car. I'm moving currently at 60 kilometers per hour. That is my initial velocity. Only problem is my initial velocity is not in the right units. So kilometers per hour, to convert it to the correct units, we had divided by 3.6. Let's just do that first. So 60 divided by 3.6. This tells me here I have 16.6 meters per second. Right. So that's actually the initial velocity. That's my starting speed. It actually takes some 30 meters to actually bring it to a stop. So 30 meters down this way here. Actually, I guess I should ask you calculate the acceleration. The displacement would be 30 here. But we come to a stop here, which is a rest. So it's going to be 0 meters. 0 meters means rest. They actually told you the displacement. I can just read that. Well, that's all in one direction. That's going to be 30 meters in front of where you started. Let's just swap that out here for actually, let's calculate the acceleration. Let's calculate how quickly did you actually step on the brakes instead. Let's find the other variables that we don't know. This time I know VI, I know the VF, which is meter per second here. I know the VF, I know the D. I can find acceleration. Maybe I use the formula v squared equals v naught squared plus 2ad. I would still write out the formula. So v squared is 0 squared is 16.6 squared plus twice. I don't know the acceleration, but it took you 30 to do it. 0, 16.6 squared. If you still have the number in your calculator, even better. So roughly 278 or so, plus 60 times a. I'm going to bring the 277 over, so negative 277 is 60a, and therefore the acceleration is this divided by 60, so 4.6. Acceleration usually has units meter per second squared. Why is this negative? Well, we've been saying a positive velocity of 16.6, positive actually implies forwards. If this is negative, that's actually implying to the left, or that actually means backwards. So I'm trying to head in the forward direction, but the acceleration is actually opposite me, so I'm going to lose. For every second that I travel, my speed drops by 4.6, so that in 30 meters I can come to a complete stop. Now that I know the acceleration here, finding the time here is actually fairly easy. You're more than welcome to use the d is vit plus 1/2 at squared. Right. I couldn't use that formula at first because I actually didn't know both the time nor the acceleration. Right. But now that I actually know the acceleration, this formula here would use a quadratic, right? Well, if I can avoid a quadratic, why not? Let's try the other one here. V is v naught plus at, a little bit simpler. If I end up getting to 0 meter per second, and my starting speed was a 16.6, if I know my acceleration was a negative 4.6, how long did I actually take to slow down? You bring the 16.6 over, negative 16.6 minus 4.6t gives us here, give or take a little bit of rounding, 16.6 divided by 4.6 gives me 3.6 seconds. And again, the more of these letters that you know, the more choices that you have in order to finish this here. Okay. We use acceleration due to gravity as a very common problem. When things go upwards, the velocity goes upwards, gravity doesn't care you try to go up, gravity always tries to pull things downwards, and then we'll deal more with that with the sort of football question later on. Only sort of trouble with these kinematic formulas here is you only have one initial time and one final time. What if I want to know the in-between? So here what we did is we actually introduced two types of graphs. One was called the displacement time graph, or a position time graph. The other was called the velocity time graph. And whenever you have like titles like that here, it's always y versus x. So your displacement time graph actually plots its displacement. Let's start off having a flag here. Our flag is 0 meters. Let's imagine the race is going up and down here. If the person is above here, if I'm at positive 1, positive 2, positive 3 like this, positive just actually implies I'm in front of the starting line, whereas anything lower than it, these, if I'm at negative 1 or negative 2, well, how can distance be negative? Distance can't. Distance is always a positive. But displacement-wise, which has direction, this one just means I'm standing behind the line. Now, I want you to resist the temptation here. Just because you're in front doesn't have to mean you're going forwards. Maybe I'm just standing at the 2 meter mark here. I might happen to be going backwards. Or if I'm behind, right, I may be at negative 3 here, I could still be going forwards. So you notice my whereabouts actually doesn't control my speed. We can actually find speed as the slope on this graph here. So the slope of a displacement time graph, I'll give you the other name here, it's called the position time graph. This one here is the velocity. So it's given by the rise over the run. So let's start off with a few segments here. Let's say the person does start off at the flag. He does this, and then he does this, and then he does this. Okay. You should be able to interpret for me the different parts of the motion here. Well, since slope is actually the velocity, the slant here is actually positive. If I try to do a rise over run, it's going to be a positive slant here. That's going to be a constant positive velocity. What's he doing in the middle? Well, during this time here, he's standing at 2. A little bit later, he's standing at 2. A little bit later, he's standing at 2. Right? He's just standing there. This right here actually implies that he's at rest. His velocity is actually 0. On a displacement time graph here, we will end up having these curved shapes. Looking at the slant here, first thing, the slant is going the opposite way. That's actually a negative slant. That means he's actually going backwards. But you notice what actually happens to the slant here as it goes onwards is it actually gets more and more shallow. So at first, I know the direction, he actually walked backwards, even though he's in front of the line, but he's actually slowing down here. And by the end of it, he happens to be back at the starting line. So the speed is given by the slope. For a velocity time graph here, this was probably a new graph to people. We're plotting his speed against his time. what would it mean if his speed is positive? If his speed was, let's say, 2, 4, 6, 8. If your speed is positive, that actually indicates the direction for you. This now does mean forwards. It doesn't imply where I am. I could be way behind the line here, and my graph could still be up here. I can be traveling forwards. If this drops below, this is actually meaning backwards. So when my speed is -2, -4, remember we just want to scale it evenly there, the negative just implies the direction. So the only time I can potentially change direction, let's say I throw an object in the air. So this object here, it's given a positive velocity, so positive means upwards, but my acceleration is actually against it. Oh, acceleration and velocity are actually opposite direction. That means I'm going to slow down. My velocity here should actually start decreasing. The slant or the slope on a velocity time graph actually gives you the acceleration. So the slope on a velocity time graph is acceleration. So anytime they ask you to calculate acceleration, you just calculate the rise over run. And basically, because the acceleration is negative, I would expect to see a negative slope. So this object here, it isn't going to stop dead in its tracks. It's going to take a little while here before coming to a stop. At the really, really top, we use that quite a lot here, at max height, we actually know what the velocity is. I'm no longer going up or down. The max height here is actually 0 meters per second. So the only time I might be able to change direction is when I switch over from going one direction and now going the opposite, from going upwards, now going in the downward direction. So that's actually where you actually change direction at potentially v equals 0. Remember, we were interested in calculating the displacement. Although I may not necessarily know where he is at any given time, I can actually calculate the displacement. Since this is just v times t, the displacement is given by actually the area under the curve. It's the area that's bounded by the curve here. So we're going to break up into these very simple shapes of triangles and squares here. If you can calculate the area, if the area is above, this is going to be a positive displacement. If the area is below, this is now going to be a negative, so it's a backwards displacement. You're actually walking backwards. For this graph here, we're going to simplify things where acceleration will be constant. It doesn't have to be 0, but being constant, there won't be any curves on this shape. But even if there's no curves on this one, we can have curves on the displacement time graph. Okay, so that one helps us analyze sort of the in-between motion, not just purely just start and finish. Okay. At this point here, we did a quick detour over into vector addition. So especially vectors were annoying because they had all these directions and we need to worry about adding vectors. Let me just do a simple question with you here. Remember, for convention here, if this were a side view problem, like our cannonball question and meatball question and whatnot, side view problem here, we have our simple up, our right or forwards, we have down, and we have left. We're just going to choose two of these directions to be positive. So up is positive, right is positive, down is negative, left is negative. If this were a top view question, which I'm going to do a vector addition question with you. So top view problem, now we have our never eat shredded wheat. In the same idea, north and east are defined as positive. We're going to come in and we're going to add a negative for west and south. So you saw us be really sloppy in this chapter. Oh, let's just add the negative. Oh, let's just take away the negative here. The negative usually just indicates to you direction. So if I already know the direction, there's no point of having that negative there. So let's try out a vector addition question. Remember, vectors have to be added head to tail. Let's say I walk at 10 meters per second in the southward direction, and then I turn 20 meters per second, 30 degrees. Let's go east of south. Right. So those are the two arrows I want to add to each other. Again, I encourage you just to pause the video. You can try it out for yourself. We have north, east, southwest, so it's a top view problem. At first, maybe this is a car or something. He's traveling just pure southward. That one's kind of nice because it's just purely vertical. I don't need to break up any components. The other one, 20, is going to be twice as long as it. And this one here is heading in the southeast direction. From the pure south direction, you start aiming 30 degrees east from there. So not only is the arrow a little bit longer, from the pure south direction, I aim that this one here is 30 degrees. Right? Maybe I was driving at the speed of 10 meters per second, and a wind actually just sort of pushed me alongwards in this diagonal. So what is my overall velocity? You'll notice when I added vectors, I put the tip of the first arrow, and I put it to the tail end of the other arrow. it's a little bit weird. Sometimes we get confused. Oh, what if I had this arrow and what if I had the other arrow? Well, I'm not here anymore, right? After I did the first one, I now have a new coordinate system. Draw the other arrow from that other point, and therefore from start to finish, here's your blindfold analogy. I know I was only going 10. Little did I know the wind is pushing me along. My overall velocity is also a vector, is going to be this one. I want to create a triangle that has this one here as the hypotenuse. Our job was, let's take this diagonal. Let's take this one here, which wasn't a nice x and y, and let's break up the components. So this is the second vector, and call it v2, v2y, and v2x. v2y is actually given by our hypotenuse I know was 20. We use our SOHCAHTOA here. This is the adjacent side to the 30 degrees, so 20 cos of 30. Make sure you're in degree mode again. v2x is actually going to be the sine. 20 sine of 30 gives us here 20 cos 30, 17.3, and then 20 sine 30, this one gives us 10. All right? And now we've actually created a new triangle. Usually what I would do is I would try to do a sum of the x and sum of the y. Actually, they're velocities, so I'm making sum of the velocities in the x, sum of the velocity in the y. Here's a key idea in this chapter here that the x does not actually affect the y. So what we're going to do, well, our first vector here had no x momentum. It was just going pure downward, so this is going to be 0. And then we have 10. Oh no, that's in the south direction. I'm going to put a negative there. So that's going to be, negative 10 here for the first vector. Right, that's in the y direction. And then in terms of the x direction here, well, my diagonal here, which actually brought me to the right, v2x is actually eastward. That one staying positive is perfectly fine. So the v2x here, the opposite side, this is given as a 10. I don't know why my numbers are sort of disappearing here. So this purple 10 here, it's a positive 10 because that's going to the east direction. And then v2y here is also going southward. So I'm going to come in and add a negative there. Right. We see based on the picture here, basically the two southward directions add together. I'm going 10 and I'm going an extra 17. So in total, this part here is going a negative 27. Why negative? The negative just means south. Right. So I know that side is 27. This side here we calculated coincidentally here to also be a 10. And I can just use my Pythagoras again. I'll let you finish off that question. What is the Pythagoras if one side is 27 and the other side is 10 squared? Find the new angle. It's no longer going to be 30. I'm actually finding this angle in here. That angle will be the inverse tan of 10 over the 27. All right? So that's a standard vector addition question. And then lastly in this chapter here, we switch over back to a two-dimensional question needing to use this sort of vector analysis here, and we did this in the whole notion of projectile motion. Okay. The one key about this projectile motion, I just alluded to it here, the horizontal and the vertical are completely independent. You can do whatever you want in the left-right direction that doesn't interfere with up and down, and similarly the up and down doesn't interfere with the left and right. So what we're going to do here, I'm just going to do this by way of example. Let's do a football style question. So this is a side view problem. I'm going to have a football starting out on the ground. I would have kicked it. I would have applied some impulse to actually get it going. But that velocity only applies for a split second. Let's kick this football here at 25 meters per second. Let's kick it up at 50 degrees. This object here is going to launch upwards and downwards from there. Let's say my friend is standing over here. A couple questions for you. Part A, I want you to find for me something about the max height. So tell me how far off the ground it is, how long. Right, so find the height. Find the time at this point. And then part B is going to ask you, well, if my friend was standing over here, calculate the range, calculate how far away he's standing. Based on the symmetry of the problem here, it is going to be half up, halfway down. And then I might ask you, well, calculate the velocity when the ball is sort of on its way downwards. And let's say the height here is actually, I don't know, let's say 25 sine 50. Let's say when it is 10 meters off the ground. So that's sort of part C. Calculate the final velocity. Okay. So we are back to using our kinematic equations. The nice thing here is start and finish are up to me. The part that's going to be constant is the initial. So I want to break out my x and y. right? I want to just sort of separate what I know about the horizontal, what I know about the vertical. The initial velocities are not going to change for A, B, or C. So only problem here is the 25 is up at a diagonal. If I take that diagonal here and I just find the adjacent side, the x part of it, that's going to be the cosine. So v initial x is actually going to be 25 cos 50, whereas v initial y is going to be 25 sine 50. I'm just trying to make a list of variables that I know for this football question. 25 cos 50 gives me 16. 25 sine 50 gives me here 19. Okay? In terms of the acceleration, yes, while I was kicking it, I'm applying some impulse, I'm giving it some acceleration. Other than that, as the ball flies through the air, we don't need acceleration for motion. And in fact, if we assume no air resistance, there is no acceleration in the left-right direction. There is an acceleration in gravity's direction, vertical direction, negative 9.8 meter per second squared. That was a gravitational field strength. Okay, so I think those are the only things that pretty much stay constant between A, B, and C. Now you're ready to do these ones here. For part A, if it's a max height question, we have one extra piece of information. The V final is actually 0. Okay, so based on that here, if you're interested in finding, well, the height and as well as the time, I want distance and I want time, go to the side that I know more, which is this side here. I'm going to calculate here what is V naught plus AT. If I know at max height, we actually hit 0. So let me just actually rewrite this here. So at max height, that one there is 0. My starting speed here, I know I launched at 25, but only 19 of it is going upwards. Negative 9.8 is physically pulling downwards from there. What's the corresponding t? You minus the 19 over, divided by negative 9.8. The time it takes is some 1.9 seconds or so. Right? For gravity to have enough time to completely get rid of your vertical velocity, it's 1.9. Well, what's the distance then? Well, now you know the time, you can actually use the d is v naught t and whatever. That formula just is a little bit harder. So let's try the other formula here. V squared is equal to v naught squared plus 2ad. Again, at max height, I'm 0 speed. V naught squared here was 19 squared, just the vertical part of the motion, plus twice. That negative is important because that means downwards, times d there. Let's just punch our way through. 19 squared is 361. I'm going to bring it over. Negative 361 is equal to negative 19.6d. The d is 361 divided by 19.6, which is 18.4. Let's just say 18 meters. Okay? So in terms of a max height question, because we knew the final velocity is 0, there we go. For the second problem here, which is the range, we're going to sort of ignore this max height question. So the Vy is not going to be 0 anymore. Let's take off our blindfold when it's back on the ground. For the total range question, you notice in the vertical direction, I'm no higher or lower than where I started because it went up and came down. The d is actually 0 when it's back on the ground. So when we're doing a range problem, B. So when we're doing this range problem here, the added piece of information that we have is no longer velocity. The added piece of information that we have is actually the d overall is actually 0. I'm not any higher or lower than where I started. So what we can do here is we can use the formula that I haven't used yet. D is v naught t plus 1/2 at squared, right? So if my d is actually 0, again, I'm still under my vertical column here. My initial y velocity here was 19. So 19, I don't know what the time is. I'm expecting it's going to be twice the time to reach max height, but let's just try it out here. 1/2 negative 9.8 with the t squared. 0 is equal to 19t minus 4.9t squared. This one would have needed a quadratic, but nicely, because we have a 0 here, I'm just going to factor. 0 is going to equal to t, 19 minus 4.9t. If I have two numbers that multiply give 0, either the first term here is 0. At t equals 0, it's on the ground. Well, that was at the beginning. That was the football starting place. Or when this term here is equal to 0, when 19 minus 4.9t is equal to 0, 19 is supposed to be 4.9t. What's the t? 19 divided by 4.9 gives me roughly 3.9 seconds, 3.8 seconds or so. And as expected, this is roughly twice the time. Okay? So you can find the time to reach there. Then you can go to the x. The same time it took for you to go up and down, right? I'm now back on ground level, is the time that this football had just to go forwards. The x velocity was boring. The x was going at a velocity of 16 to begin with, and you now just give it a time of 3.9 seconds. D is equal to vt, and we're going to go 16 times it by, oh, you travel for 3.9 seconds in the horizontal. What is my range? What's the ground that's covered? Give or take about 62 meters or so. So it's the same kinematic formulas, but we're actually using sort of the x direction and the y direction here. I'm just going to hint you at how do we do C. I'll leave this for you to try here. For C, we're neither at max height nor we're on the ground. What they gave you here is my distance here is actually 10 though, okay? So this is a vertical distance. So if my football here is 10 meters higher, notice I'm going to have 2 points that actually give me this answer. The football was 10 meters higher here, 10 meters higher here. I'm looking for the one that actually has a negative y velocity because it's actually going downwards. So for this part C, I'm just going to hint at it here. When I am 10 meters above the ground, right, that 10 meters here is vertical, so I'm expecting to look at the vertical side again. What if my d was actually equal to 10? Would I be able to calculate the final velocity? Well, let's try out our first formula again. V squared is V naught squared plus 2AD. I don't know what the final velocity is. I know I started off going 19 plus twice negative 9.8, and they just randomly give me a 10 here. Let's just see what happens to the math here. V squared, 19 squared plus 2 times negative 9.8 times 10. This one here gives me 165. The v could be the root of 165. It could be either positive or negative 12.8. Why do I have two answers? Well, like I mentioned, just being 10 meters off the ground could be you're on the way up, you're going 12.8 up. The one that I'm looking at in my picture is I already went up, I already went positive 12.8 there. I'm actually going negative 12.8 here. So I'm actually going to take the negative answer this time, just based on the problem here. If my v final is actually negative 12.8, then it's a very simple matter. Well, the x hasn't ever changed. It's just 16 meters per second. On the way downwards, I'm actually going 12.8. See if you can just do your Pythagoras one more time. Find the overall velocity, find this angle here. The angle will be described as below the horizontal, because this one here is a side view question. It is not south of east. Okay, so practice through some of those questions. Hopefully that's a nice recap for you. Thanks, guys.